Hi, Tom Walls, Carbide Processors. Here with Lucky the dog, who can't figure out why we haven't left for the park yet. But anyway, I had a couple of calls in the last couple of weeks about snap shoulders on saw blades. And basically, the shoulder runs from, let me find something here. There's a ruler. The shoulder runs from here to here, in through here. And what happens is this whole thing snaps off. All right, there's a couple of things here. Sometimes the saw tip just comes off clean. That's bad brazing or bad carbide preparation. Anymore, it's usually bad carbide preparation. Sometimes, if you hit something real hard, the carbide will break and part will come off, but part's left in there. Sometimes, if the steel is really, really soft, it'll actually tear or rip. Highly unusual. You can go your whole career with I've ever seen that. Sometimes the steel will snap. It comes off clean. I've seen saw blades where whole sections came off. That was near the end of the old Systematic. Long story there. But anyway, what happens is saw steel reacts to heat. Let's use hardness measurement as Rockwell C-scale. And saw steel, roughly, call it mid-40s, okay, 42, 46, depends on who and what and the applications and what the filer likes, what the saw builder likes. If you tell me I'm wrong, the ideal Rockwell is whatever, fine, I'll agree with you. Anyway, for the sake of argument, figure it's the mid-40s. So this saw steel is supposed to be mid-40s, which is a combination of strength and hardness. If you overheat during the brazing, you can bring it up as high as a Rockwell 60. At Rockwell 60, the saw steel is really hard and it's really brittle. When you braze a saw tip in, if I stand up, we've got a white background. Can you read the t-shirt? All right. Anyway, when you braze it in, you should be directing the heat in through the carbide tip into the steel. What happens, especially with induction, but also with a torch, the steel responds much, much better to heat than the carbide does. With a torch, figure maybe 3 or 5 to 1. With induction, figure the steel's about 10% more magnetically susceptible than the carbide. So in order to bring the roughly, in order to bring the carbide up to temperature, you'll bring up about 10 times the weight of steel to temperature. What you want to do is put a pre-tin tip from Carbide Processors. Hey, it's my video. Anyway, put a pre-tin tip from Carbide Processors in here. You heat through the carbide, through the braze alloy. You heat as little of the steel as you can. And the reason for that is that the steel you heat is going to get hard, it's going to get brittle. At brazing temperatures, it just does. If you can control the heat affected zone into this area right behind the steel, and you have to get the steel as hot as the melting point of the braze alloy, because that way it bonds properly, it forms an intermetallic, you get a super strong bond. If you don't do it, you get a cold joint, and typically it stays on until you run it and then it comes off. If you heat here, and you can see in the drawing on the blog where they've got an induction coil, and the induction coil, one loop comes down around the tip and the other loop comes down around the steel. That way what they've done is they've heated all the way back to here. The problem with that, when you heat it all the way back to here, you get a chill line, whatever, you'll get a color change too. Typically the heated area gets stripes in it, kind of a rainbow stripe. The area where the hard steel, the heated steel, meets the softer steel is called a chill line. And there's a couple different definitions for that, but the one I just gave you is ballpark. Other people may have slightly different versions. Anyway, when the saw runs, the impact, the saw is running this way, so the impact is coming this way. If you have a little bit of hard, brittle steel back here, but you have a big, strong, soft shoulder behind it, you're good as gold. It'll run just fine. If you let the heat get all the way back here, you get a heat affected zone back here where you get embrittlement. What happens, particularly if a saw with, I don't know how many this has got, but if you get a saw with more teeth, you have consequently smaller shoulders. When it hits here, it pushes back on this. Where you have a transition zone, and most of you people watching this are incredibly good mechanical, so you'll understand this. When you have a transition zone, you have a weakness, sort of like where if you have a smooth curve, it's equally strong all the way across. If you have a curve with a kink in it, then the weakest point, it's going to bend, it's going to break at that kink. Sort of the same idea here. So when this hits something, as it will, it's more likely than not to snap the whole shoulder off. There's a couple ways to test this. Yeah, here they are. Here are a couple of plain files. One's a triangular file and one's a round file. The best way to test it is to take it and just rub it across and see if it grabs. See if it grabs or slides. Again, if you've never filed steel, try it. The difference becomes apparent immediately. Those of you that, well, we've got a customer that cuts rock in Montana, Montana Rock Works. They have 4-foot across saw blades. The steel bodies are huge things. Cutting rock is really, they replace them a lot and they use the saw blades for months. What happens is the steel in here work hardens. And Don Wallinger, as a matter of fact, in the video taught him this. If you get a work hardened notch, you give it the file test, take a Dremel or something and grind it out till it's soft and you can get it anymore. With the two files, the triangular one is sometimes preferred because it grabs more and some people feel it's more sensitive. However, when you do as I just did, and this is a plate that's never going to be run, when you do as I just did, what you've done with the sharp triangular edge is created a notch, which is a stress point. More properly, it's a stress concentration point. In any case, it's a discontinuity in a smooth curve, and just as we said earlier, this is where the trouble's going to start. So this is an invitation to a crack or a crack or a tear in the steel, and it might be a tear because now we're looking at the 40 Rockwell steel. So the round one is, if you're going to run the saw, the round one is far and away preferred. I would not use the triangular one on a saw blade that's ever going to be run. Prevent embrittlement, go see our video on how to braze saw blades, part 1 and part 2. Don Wallinger does a beautiful job in part 1. The Hartleys do a beautiful job in part 2. Hartleys use a different flame and they've got an entirely different technique, but neither one of them has any problems. They both get 100% results, so that's hard to argue with. Anyway, that's some information on embrittlement and saw steel, and as I say, that's come up a couple times lately, and I don't know why, but there's some things. More online. Feel free to call me anytime you want, and we'll kick it around if you have a problem. Thank you. Bye.